Good morning. In this lecture, that is in unit 2nd, there are some definitions. Today's lecture, we will see the definition of normal space, T4 space, completely normal space, Eugen's lemma, Eugen's function, and perfectly normal. Some results on these definitions and examples on this definition. Now we say we know normal space. Normal space, that is in topological space X, there are two closed sets A and B. That is A and B are disjoint closed sets. If there exist two disjoint open sets U and V such that A is subset of U and B is subset of V, then X is normal space. Next definition is T4 space. Normal T1 space is called T4 space. Now again we know definition of dense set, that is D is subset of X, topological space X. D is subset of topological space X, and this D is called dense if it contains all its limit points. What is limit points? Limit points, that is here D closure equal to D. And D is dense in X means D closure equal to X. Now there is one result, that is lemma. Here if X contains dense set D, and here again X contains S, here S is closed, relatively discrete, and subspace of topological space X. And if relation between D and S here, that is coordinate of S is greater than or equal to 2 raised to coordinate of D, then this X is not normal. This result is there. Next, one more result, that is normal space need not be regular. One more result, every T4 space is Tikna space. Every T4 space is Tikna space. We know Tikna space is completely regular T1 space, that is T3 1/2 space. Every T4 space is Tikna space, but converse of this result is not true. That is Tikna space need not be, converse is not true. Tikna space need not be T4 space. And for this, here we take example of again Murray plane, that is gamma. Murray plane. This Murray plane is Tikna space, but this is not T4 space. That is T4 space means normal T1 space. Now next result, next example, every metrizable space is T4 space. Is T4 space, and every cube is normal. Every cube is normal. Also, one more result is, that is, every pseudo-metrizable space is, every pseudo-metrizable space is normal. Your definition of normal space was, that is, a topological space X is normal if and only whenever A and B are disjoint closed sets in X, then there exist disjoint open sets U and V with A is subset of U and B is subset of V. Normal T1, then this X is normal, and this normal T1 space will be T4 space. Now, lemma 15.1 was the definition of normal space and T4 space. Now 15.2, there is 15.2, there is lemma, that is, if X contains a tensor set D and X contains a closed relatively discrete subspace S with coordinate of S is greater than or equal to 2 raised to coordinate of D, then X is not normal. Here result is X is not normal. Now next examples, that is, normal space need not be regular. There is example, and here every T4 space is Tikno space. Every T4 space is Tikno space. But Tikno space need not be T4. An example is, that is, gamma Murray plane is Tiknos, but gamma is not normal. Next example is, every metrizable space is T4 space. And one more example, that is, every pseudo-metrizable space is normal. Next, we know results about subspace, product space, quotient space. Now, in this normal space, that is for T4 space, different result is there. Now up to this, that is T0, T1, T2, T3 space, every subspace of dash space, that is T space, is T space. But in this T4 space or normal space, result is arbitrary subspace of T4 space need not be T4. But there is some result, that is, which that subspace of T4 space is T4 space, that is, there is condition, that is theorem 15.4. Result first, a closed subspace of T4 space is T4. Closed subspace of T4 space is T4, and we know normal T1 space is T4 space, and for subspace the result is true for T1. Now here closed subspace of second result is about normal, that is, closed subspace of normal space is normal, and that result for arbitrary subspace of T4 space need not be T4. Again, for product space, product of normal space need not be normal. And for this, there is example of Sargent-Free line, that is, product of T4 space need not be T4. Example is Sargent-Free line. we know Sargent-Free line is T4, but here E cross E is not normal. In this example, what is this Sargent-Free line? That is, this is real line with basic neighbors of X are the set of the form close open interval xz. Obviously for z is greater than x, that is x is left side of the real line and z is the right side of the real line. This, in this result, E, that is E cross E is not normal, but its factor space, that is E, is normal. Therefore we can write here product of T4 space need not be T4. That is, Sargent line E is T4, but E cross E is not T4, or not normal. Now for quotient space, result is arbitrary quotients of T4 space need not be T4. For quotient space from first T0, we know quotient space of dash dash space need not be dash dash. This result is true for T4 up to T4. That is, here we take word arbitrary. Arbitrary quotients of T4 space need not be T4. And in previous T space we use the non-empty quotient space or subspace. Now next result is the closed continuous image of normal space is normal. And again, the closed continuous image of T4 space is T4. This result is again true. Now next is the Urijan's lemma. By using this Urijan's lemma, we take definitions of Urijan's function and perfectly normal. Now in Urijan's lemma, the space X is normal. And again, for definition of normal, we take two disjoint closed sets. Again, here for this definition, for this Urijan's lemma, a space X is normal if and only whenever A and B are disjoint closed sets in X, then there exists a continuous function f from x to I is again closed interval 0 to 1, with f of A equal to 0 and f of B equal to 1. This is Urijan's lemma. And in this lemma, when we define such a function, then function f is called Urijan's function, and for inverse of this f of A equal to b 0 and f of b equal to 1, that is, it is inverse for all inverse. This is not true, but in here if we write A equal to f inverse of 0 and b equal to f inverse of 1, then this x is called perfectly normal. That is definition of Urijan's function. If A and B are disjoint closed sets in normal space, a function of type whose existence is guaranteed by Urijan's lemma is called Urijan's function for A and B. And next definition is perfectly normal. That is, if it is not in general true that given disjoint closed sets A and B in normal space, there will be a Urijan's function such that A equal to f inverse of 0, B equal to f inverse of 1. The spaces with this property are called perfectly normal space. Now Tit's extension theorem, that is last article of this unit. Tit's extension theorem, X is normal. Tit's extension theorem, X is normal if and only when A is closed subset of X and f from A to R is continuous. Then there is an extension of f to all of X, that is, there is a continuous map capital F from X to R such that f restricted to A equal to f. This is Tit's extension theorem. That is, this is the extension of f, small f. in capital, that is here A is closed subset of X, and all, that is there is extension of F to all of X. This extension defined by, that is F, that is here we can write here F as F restricted to equal to small f, that is X must be normal. Here that is X is normal if and only if whenever A is closed subset of X and small f from A to R is continuous, then an extension of small f to all of X, that is there is a continuous map capital F from X to R, so that F restricted to A equal to F. Now in next lecture we will see definition related to neighborhood base, countable neighborhood and countable neighborhood base. We know this definition in topology first, and by using these definitions we will take the definition of cover, that is cover, subcover, open cover, shrinkable cover, point finite cover, first countable space and second countable space. For this you must see definition of neighborhood and neighborhood base. Thank you.